All right, so now we have we've really done the bulk of the work of understanding how we set up and solve Newton's first law and Newton's second law problems, so the dynamic and the static and the no net force and all those different types of problems. And we did that one in the last two sections. And now in the rest of this chapter, really, what we're going to be doing is taking a look at some of these forces that we already introduced and going a little bit more in depth to understand them a little bit better. And the way we're going to start is we're going to take a look at weight and apparent weight. So we know we all have weight. We'll talk about a formula for that, but we also have an apparent weight, and we'll get to talk a lot about that as well, both in this chapter and in the next. So this pre-lecture video, it's about a 7-minute long video where he's taking a look at the concept of weight and apparent weight. And one of the best ways you can do that is by going into an elevator. And in an elevator, depending on the direction you're moving and whether you're speeding up or slowing down, your apparent weight actually changes. And you know that this is true because if you go into an elevator, you get these weird feelings when you're riding up or riding down the elevator. So sometimes you feel like you're getting scrunched together. Sometimes you feel weightless or light, like you're floating in the air. And that's due to the net force of caused by the acceleration, and that is what changes your apparent weight. So in the pre-lecture video, he goes into great detail about this, and it's a good video to watch to take a look at that. Okay, so the first little section we're going to talk about is the difference between mass and weight. We'll talk more about apparent weight in chapter 6 as well, and right now, but we're focusing on the concept of mass and weight. So mass and weight, although commonly interchangeable in the physics realm, are really not the same thing. So mass, when you first learn about mass, probably in elementary school or middle school, mass is how much stuff makes up an object. Now, in physics, we go a little bit different, and we say it's a quantity that describes an object's inertia. And the reason is it doesn't matter where you are, you always have the same mass. You could be in the middle of space and you'll have the same mass. Weight, however, weight is a gravitational force. It's the force of gravity, and we've talked about that. We said that weight is equal, or can be also described as the force of gravity. And we'll talk more about the gravitational force in chapter 6 as well. But for right now, we're just saying our formula for weight is mass times gravity. And you see that I have that little negative sign there, and that's because the weight force is always straight down to the center of the Earth. And the weight, in this case, is the only force acting, so the net force is the weight. This would be an object that's in free fall. So when we're going in between weight and mass, the really easy version is for us to just say mass times gravity and just add a 0 at the end of the mass, because we just say gravity is 10 meters per second squared. It makes it really easier. This is just a really a basic table of conversion factors going in between mass, weight, and force, and not something that we'll spend really any time with because we just use the metric system anyway. So let's start off with a quick little example, and that is what are the weights in newtons and the masses in kilograms of a 90-pound gymnast, a 150-pound professor, and a 240-pound baseball player. And I'm sorry, football player. So in this case, we're just looking at doing conversions. So I'll just set up the first one. So if we're looking for the weight of the gymnast, well, it's 90 pounds. And if we're converting into newtons, 1 pound is 4.45 newtons from that conversion factor. Again, I'm not going to make you do this really ever, and that's 400 newtons. That's her weight in newtons. The mass, I would do the same thing, except now it's 90 pounds. And 1 pound is 0.0454 kilograms, otherwise known as, the way that I always learned it was 1 kilogram is 2.2 pounds, but either way, 41 kilograms right here. So kind of just a quick little video, or a quick little reminder in unit conversions, not something that's going to be super important in this unit. And here are all of the answers for those objects as well. So if you need to quick go through them, you can pause the video here. So now that we know what mass and weight are, let's talk about apparent weight. Now, apparent weight is, in physics, it's the weight of an object. The weight is the force of gravity on the object, but apparent weight is your sensation of it. How do you feel in that situation? Your weight does not change, but your apparent weight, it absolutely changes. And our definition in physics is the magnitude of the supporting forces, supporting contact forces. And really what that equates down to is it's your normal force. And your normal force can actually change based on your acceleration. So we'll take a look at that again throughout this chapter, as well as chapter 6, which is all about circular motion. You think about being in a car and going over a hill, and you feel this lightness, this weightlessness. That is because your apparent weight is changing. So when you're in an elevator, there's a few different forces acting, right? We have just the normal force and the weight. That's it. That's the only forces acting on you. And the normal force, whenever you're, in this example, you're going up, right? So your acceleration is up, so your net force is up. So your normal force has to be larger than your weight. So the normal force then is the weight, because it counteracts that going down, plus your mass times acceleration, which is the net force. So this concept right here, this is F net. So the net force plus your weight is your normal force, and that is your apparent weight in this case. So this feeling that you get when you're in the elevator is your net force, or I'm sorry, your apparent weight. Now, when I think about this, when I first go in an elevator and I push the button to go to the top floor, I feel like I'm being compressed, or I feel heavier. And the reason that I feel heavier is because I have a larger apparent weight as I go up the elevator. Why this happens? Well, Newton's first law says an object at rest tends to stay at rest. So your inertia actually wants you to stay at rest, but the elevator pulls you up, and you have this resistive force, and that makes you feel heavy. Conversely to that is when you're at the top of the elevator going down, or you're going up, slowing down. There's a few different things, but when the elevator comes to rest, my body wants to stay in motion. So as the elevator slows down, as I'm going up, I feel weightless, or I feel light. Okay, so we're going to do another example problem. We have somebody is standing on an elevator that's moving at 5 meters per second. So we know it's moving. And it says Anjay's mass is 70 kilograms. So we know regularly his weight is 700 newtons. So this 70 kilograms right here, his actual weight then is 700 newtons. We just add that 0. But as the elevator stops, it reads 750 newtons. Okay, so that means he feels heavier than what he normally does. So in this case, if he's already moving and he feels heavier, that means that I need what we just talked about, our apparent weight, is going to equal the regular weight plus mass times acceleration. This means that this acceleration needs to be positive. So if I'm going up at 5 meters per second and then slowing down, because we know it's slowing down because as the elevator stops, then that would mean that I would feel lighter. So what actually is, I'm going down the elevator, and as the elevator slows down, I get this greater apparent weight. So that answers half the question, but it also asks, how long did the elevator take to come to rest? Well, for that, we're going to need the acceleration so we can solve for that. So let's go ahead and do that. And if I look here, the acceleration then is going to equal the apparent weight minus the regular weight divided by the mass, which is 750 newtons minus 700 newtons divided by 70 kilograms. And I get 50 newtons divided by 70 kilograms. and I get an acceleration of 0.71 meters per second squared. So with that acceleration, I can go back into kinematics. I have VI is VI is 5 meters per second. VF is going to be 0 meters per second. And then my A is 0.71 seconds. And I can use kinematics to solve for that. And I will let you go ahead and do that or check out a later slide. But we get about 5.5 seconds. So here is, again, the work to set up the math for the acceleration. You can see that in this example, however, they did use the 9.8. So that's why we get a slightly different acceleration. And using the kinematics, VF equals VI plus AT, we get a time that it takes of 5.5 seconds to come to rest. So this concept of weightlessness then is a great application. And if you haven't ever seen this before, this is known as this plane right here. It's a NASA plane. It's known as the vomit comet. And the reason is well, people tend to throw up. They must be teaching physics up there. But a person, when they're in free fall, so this vomit comet, they go up really, really, really high, and then they nosedive so that the people inside feel like they're in free fall, like they're skydiving essentially, but they do it in such a way that they're floating around inside the plane. And the reason that they do that is that it simulates a zero gravity situation. Now, that's not actually a good terminology, zero gravity. An object that is in free fall appears weightless, not because it doesn't have weight. There is still a gravitational force that's pulling it down. The reason it feels weightless is because there's no apparent weight. There's no normal force. You have to have a normal force to feel like you have weight. So that it's a thick concept in physics, but an object that is weightless has no apparent weight. It still has weight. Gravity is still pulling it down, but it appears weightless because there's no supporting forces. This is actually Matt Herr. He's a instructor at Platteville. He got to go on the Vomit Comet, and he got to test his GoPro camera stabilization system. So he made his own GoPro camera thing that holds a GoPro but stabilizes around him as you're in free fall in space. So pretty cool. He's a high school physics teacher out in Platteville, but he got to ride the Vomit Comet to test out some stuff. All right, so we're gonna follow up with a quick check. It says a 50 kilogram student gets in a 1,000 kilogram elevator. Hey, spoiler alert, that whole 1,000 kilograms, we don't care how much the elevator weighs. It rests and stands on a metric bathroom scale as the elevator accelerates upward. So as he goes up, he's accelerating up. He has positive acceleration. Therefore, his apparent weight will be greater than 490 newtons. Okay, next one. Now, same thing, and sadly, it says the elevator cable breaks. What is the reading on the scale during the few seconds it takes the student to plunge to his doom? Well, in this case, we're again in free fall. So if he's in free fall, there is no apparent weight because there's no supporting contact forces, and he has a 0 Newton apparent weight. He feels weightless. He's in free fall. So there's an extension, and occasionally it pops up on the AP exam, but it's inertial mass versus gravitational mass. Now, your mass never changes. Your weight changes depending on the planet that you're on because it's a gravitational force. The concept of mass, however, does not change. But how we get it or how we solve for the mass can change. So inertial mass versus gravitational mass. And essentially all this means, if we take a look at our AP equation sheet, anytime that we have mass in a problem or in a formula, such as looking at the weight, right? So if I know the scale reading of an object, like a spring scale or a scale that I'm standing on, then a spring scale pulling down, then I know that this is a type of gravitational mass because it depends on free fall acceleration. However, if I'm in space and I am stretching a spring out, which we'll talk more about later, and I let it oscillate back and forth, which we'll talk about more later, that actually does not change from planet to planet. So that's what we refer to as its inertial mass, because it never changes. The inertial mass is doesn't rely on gravity to solve for it. So gravitational mass uses G. Inertial mass does not use G. So it's just a quick little extension. We may or may not see a problem like that throughout the year or sometime during the year. But just a heads up, when we talk about mass, that's something we're talking about. All right, so that's actually it for your introduction into mass and weight. We will continue in the next section to continue to break down forces and in the normal force, and we'll do that in the next section.